In this video, we're going to continue our informal investigation of limits, and we're going to look at a couple of examples where we're given a formula. These examples are rational functions, and we're going to look at the formula, use that to help us maybe get a graph using some graphing technology like a graphing calculator, and maybe a table of values, also maybe using a graphing calculator. And using the table and the formula and the graph all together, we'll use that to kind of help us get some ideas about limits and some other things that are related to the function. So let's take a look here at this first example. F of x equals 1 over x. And we're going to try to answer these questions. And what I'd like you to do is try to maybe answer these on your own first, and then come back and maybe check your work as you go on. So first question is, what is the domain of this function? Then see if you can make out a table or tables, portions of the table of the values of this function. And we're going to use that to examine the behavior of the function near any x values which are not in the domain. And we're going to use the table to make a conjecture about one-sided and full-sided limits as x approaches these values. And then also use tables to help you determine the end behavior, that is, the limit as x approaches infinity and the limit as x approaches negative infinity. And then look at these two tables and tell us what do these things tell us about the graph. And then actually maybe have an idea of what the graph looks like before you graph it on your graphing calculator. And then go ahead and actually maybe graph it with the graphing calculator and make sure that this agrees with what you saw before in the table and what you felt would happen basically just looking at the function formula. Okay, so I'd like you to work on this one just a little bit. Maybe you've looked at this function in the past, so this shouldn't take you very long, hopefully. And come back when you're ready and we'll go over this. Press pause now. Okay, so we're looking at the function 1 over x. Okay, and the first thing is, the first question is, what's the domain? Remember, the domain is all the set of all input values for this function, and we assume it's the largest subset of the real numbers that works. In other words, start with the set of all real numbers and throw out the bad stuff. What's the bad stuff? It's anything that makes this function undefined. And of course, the only thing, it's really a one-step function. We're just dividing 1 by whatever x is. The only thing you can't divide by is 0. So the only thing we need to throw out is 0. So the domain is everything except for 0. Everything else is good. So the domain is the good stuff, the stuff that actually gives us points. So we could say the domain is the set of all real numbers except for 0. The easiest way to write that is use this symbol here for r. If we write that by hand, we'd write it this way, the symbol for r, and we want to take away certain points. One point is actually just the point 0. So that's how you would write it by hand, right here. And of course, in the calculator or the computer, we'll typeset it like this: an open-faced r minus 0, the set containing 0. If you did it in interval notation, you'd have to go from forever left, negative infinity, up to 0, union 0 to infinity. Notice there are round parentheses everywhere, so of course we never include infinity or negative infinity, but notice we never include, we don't include 0 in this particular case either. So the domain is everything except for 0. So 0 is kind of an interesting point. It's not a point on the graph. So x equals 0, of course, is a vertical line, specifically the y-axis. So we know this graph doesn't touch the y-axis, but what does it do near the y-axis? That's going to be an interesting thing to look at. So let's look at that. And notice, of course, again, it's undefined at x equals 0. So here we're approaching 0. 0 is right in between here. It's not actually in the table. And again, I've taken these x values, as I've done in the previous videos, and I've arranged them going left to right on the number line. And we see that we're coming in from the left side here, getting closer and closer to 0. And over here we're coming from the right side, getting closer and closer to 0. And notice when we put in 1/10, negative 1/10, the reciprocal of that is negative 10. Negative 1/10 is negative 0.1. Reciprocal is negative 10. And you put in negative 0.001 or negative 1,000, excuse me, the reciprocal is negative 1,000. If you put in negative 0.00001 and do reciprocal 1 over x, you get negative 100,000. And I think you can see as you let these x's get closer and closer to 0, the y's get closer and closer to, well, they don't get closer and closer to anything. They keep getting smaller and smaller without bound, further and further into the negatives, larger absolute value, but negative. And so we would say that that limit from the left is negative infinity, which we would write this way. Now that says that if you look at the y-axis, this is going to be coming down this way on the left side, going down towards negative infinity. Similarly, if we go from the right side, we would put in 0.01. 1 over x is then 100. If x is 0.00001 or 100,000th, then its reciprocal 1 over x is 100,000. And here we have 1 millionth input and 1 million output, so the y's are getting bigger and bigger without bound. So we say the limit as x goes to 0 from the right side is positive infinity, so the graph is going up like this. And so we have a vertical asymptote there of x equals 0, or the y-axis. Now if we look at our end behavior, and we let x get bigger and bigger here, x is 10, 100, 1,000, and so forth, then 1 over that is, we're getting smaller and smaller. So this thing is going out here, approaching the y equals 0, which is the x-axis, as we go to the far right. And of course, similarly, as we go far to the left, we'd be putting in negative values, getting larger and larger in absolute value, but negative, that goes further and further to the left, like negative 10, negative 100, negative 1,000, negative million, negative billion. And we see that the y's get closer and closer to 0, and so the graph is going to look something really rough sketch like this picture here. And then we can maybe graph that. I use Graphmatica. You could use maybe a calculator to graph this, and we get a nice looking picture here that looks like this. And you can see the features on this like we predicted. So for example, that we have to, now if you're actually going to plot one of these by hand on a piece of paper, you have to actually look at the values and put some dots on there. You know, when x is 1, y is 1. When x is 2, y is a half. 3, 1/3. 4, 1/4. 5, 1/5. 6, 1/6. 10, 1/10, and so forth. 1/2. 2, 1/3. 3, 1/4. 4, and so forth. And plot some points so that you can see that. Okay? So that does agree with what we had there. Okay, let's try one more example kind of similar to this. F of x equals 3x minus 21 over x squared minus 49. So first of all, again, tell me the domain. Then particularly for points that are not in the domain, is what happens nearby those points. We know any x values that are not in the domain, when we graph x equals that number, whatever it is, we get a vertical line, and we know the graph of the function does not touch that vertical line. But does it approach a single point on that vertical line, or does it approach that vertical line asymptotically, or is there something else going on? Let's see if we can figure that out. Okay? So what, if any, are things that are left out of the domain? The domain, of course, is the stuff that's good, that's left over. Then make some tables investigating the limits as it approaches things that are not in the domain, and then also the end behavior limits as x goes to infinity and negative infinity. See if you can tell what the graph's going to look like before you actually graph it, and then use a graphing calculator to draw a graph. So work all that out on your own and come back and check your answers here in just a minute. Press pause now. So here in this case, we're looking at this function, 3x minus 21 over x squared minus 49. Now before I go any further, I'm going to actually just look at the formula a little bit. And of course, there's not going to be any trouble multiplying x by 3 and subtracting 21. There's not going to be any trouble with squaring x and subtracting 49. You can do those two things for any real numbers. It's the division that could give us a problem. And specifically, we can't divide by 0. So to be able to see what makes the denominator 0, it's going to be useful to factor it. So the denominator is x squared minus 49. That's x squared minus 7 squared. So that factors, that difference of two squares factors as our sum and difference pattern, x plus 7 times x minus 7. Check that out by FOIL and notice that that does work out. FOIL anagram for the distributive property here. Now we're also going to use the distributive property to factor out the numerator, 3 times x minus 7. Now don't reduce yet. Look at the denominator, the original denominator, x squared minus 49, or x plus 7 times x minus 7, and we see that if x is either negative 7 or positive 7, that makes the denominator 0. So both of those numbers have to be thrown out of the domain. So the domain is all real numbers except for negative 7 and positive 7. And that's a typo. Let's see if I can fix that real fast. Should be a negative. There we go. Negative 7 and positive 7 are both thrown out, all real numbers except for that. And so if interval notation, if we had to do that, we go negative infinity to negative 7, union, negative 7 to 7, union, 7 to infinity, and notice we've skipped over 7 here and negative 7 here. I like this first notation a lot better. It's a lot more compact, particularly when you're writing several points that have to be eliminated. So we're interested in what happens near 7 and near negative 7. Okay? And so first of all, let's look at what happens. Well, first of all, I want to look at this from an algebraic standpoint down here. Notice if I factor this out, the x minus 7 cancel, and you get 3 over x plus 7. And that's true as long as x is not equal to 7. So these two are equal for anything where x is not equal to 7. So I can look at near 7 or negative 7. And here I'm going to look near 7 first. So if I look at this, the formula up here, again as before, I'm placing 7 kind of somewhere in the center here where it's not really on the graph or in the table. But we're letting the x's come in from the left side closer and closer to 7, and the x's come in from the right side closer and closer to 7. I've arranged the x's in increasing order from left to right. And then we look at what the y's do. So maybe it's not completely as easy to see what's happening here, but it looks like this is coming into about 0.2142 something, maybe 8 or 9, a little bit harder to see there. We might look at it a little bit more closely. Well, if you look down here, in this version, we might be able to see exactly what it's getting closer and closer to, because this function is the same. And if we look at a table, let's see, now I'll look at that in a minute. Yeah, here we go. Here I put in the reduced version here, and we notice that these two, the tables are exactly the same. They both give us an error message when x is negative 7. But when x is positive 7, we get an output here for this one, but an error message in the original. Okay, well, what does that mean for us? Well, that means that this value here, or that's approximation of the value, is the value we get when we plug in 7 here, which is 3/14. Okay, see what 3/14. If you try to make that to a decimal, that is 0.21428 57, and then it's 1/4, then it repeats. It actually is, I know when I divide by 7, we often get a 6-digit repeating pattern. So that's the exact value right there, 0.2, then 1/42857, 1/42857, 1/42857 forever. In other words, 3/14 is the actual limit value. And this is approximately 3/14 that you see right there in the table. So that would be the output value. That point 7, 3/14 is an actual point on the reduced graph, y equals 3 over x plus 7. But it's not a point on the original, so that's actually a hole in the graph. Okay? Now, and we can see that that's what it's basically approaching there, is that hole. let's look at what happens as we go to negative 7. A very different situation happens there. As we're approaching negative 7 is somewhere in here in the between these parts. We're coming from the left or from the right. Look what happens. The y values aren't approaching a particular number. As we come in from the left side, these y values are getting smaller and smaller, more and more further away from the x-axis, right? Going way further down, decreasing without bound, and they're increasing without bound coming this way. So the limit from the left side is negative infinity and positive infinity from the right side. Error messages on both the original or the reduced version when we look at the tables side by side. And so right here we have a vertical asymptote. Hole in the graph is indicated by this situation here, where we have an error in the original but a number in the reduced. Error both places, in this case, works out to be a hole in the graph. Or both places was a vertical asymptote. So, what does that tell us on the graph? Well, that tells us that if we are approaching, we know it's not going to touch the graph at x equals 7 or at x equals negative 7, but when we look at the graph, as it approaches negative 7 from the left side, it's going down forever, and negative 7 from the right side is going up forever. As it approaches x equals 7, it actually approaches a specific point, and that point is down here somewhere, 3/14. So maybe it looks something like that. Okay. Now what happens as we go to infinity or minus infinity? Well, here we let x go to infinity. It's getting larger and larger without bound, and look at the y's. They're getting smaller and smaller. It looks like they're getting closer and closer to 0. And similarly, if we let the y's get further and further out to the left, the x's go further and further to the left. The y's are getting closer and closer to 0 there. So both of those limits are 0, and so we see that on the graph here. This is the point 7, what was it again? 3/14? Yes, 3/14 is our hole in the graph. And this vertical line right here, y equals negative 7, is our vertical asymptote. So you can see the difference there in the vertical asymptote and a hole in the graph. Now if you graph this on your graphing calculator, this hole may not show up very well. If you try to trace it to 7, you'll get an error message, or if you look at the table, you'll get an error message in the original function. And then side by side, you'll see the hole as when you do side by side tables here. Again, for x equals 7, one is an error message in the original, but a number in the second one. That's a hole in the graph. And for a rational function, if you get an error message both times, once you've reduced it and in the original, that's going to be your vertical asymptote. And of course, you'll be able to see the vertical asymptote here. Now, sometimes when you graph these on a graphing calculator, you'll see something that looks like, you'll see it, depending on your window, you may see it come down and then go up and kind of connect up like that, where it's connecting them up. Of course, we know they're not actually connected. That's the graph kind of lying, calculator kind of lying to you there a little bit, because you told it to connect up these things, and they shouldn't be. And so it really should be three disconnected pieces. One over here from negative infinity up to negative 7, then a connected piece from negative 7 to positive 7, and then a hole in the graph, and then a connected piece from 7 on out. Okay, so that gives us a couple of examples of rational functions where we were given the formula and we were able to use tables and a graphing calculator or Graphmatica or something to come up with limits and to examine a little bit more what the graph looks like.